it's planar, we're assuming, and from the structures that we showed earlier, it's conjugated. All of these carbons are sp2 hybridized, and so there's continuous p orbitals around the compound. And the number of pi electrons here now, we have to consider, so each double bond here, there's 2 electrons in the pi system, in the p orbitals from each double bond. So we would have 2, 4, 6 pi electrons. Let's write that down. So we have 6 pi electrons. Now we have to see, does that meet one of these outcomes of Huckel's rule? So if n equals 1, it's going to be 4 plus 2, that would be 6. So it would match that. So with Huckel's rule, this is going to then be considered an aromatic compound. So this Huckel's rule of 4n plus 2 is not just a random choice of numbers, but this is actually, it fits to allow the electrons to fill the bonding molecular orbitals in these different compounds. Now, in terms of something that's anti-aromatic, the definition actually is a little more complicated than I'm making here. I'm simplifying. But one way of thinking about it is that rather than meeting 4n plus 2, the compound will have 4n pi electrons. It's going to meet these other criteria, but rather than 4n plus 2, it would meet 4n in terms of the pi electrons. And that would be defined as anti-aromatic. The reason I'm simplifying is that you actually are technically comparing the compound of interest to the non-cyclic equivalent compound, but we're not going to really do that. But now let's see how a few of these other compounds actually match and if they're aromatic or not. So if we first take our 3 at the top, we said these are not aromatic. And so that means they're not going to meet one of these first 3 criteria. So butane is not cyclic, so we can stop right there. Cyclohexane, it's cyclic. We know it's not planar, right? It's actually in the chair conformation, nor is it conjugated. All of these carbons are sp3 hybridized. So we can just stop right there. We don't have to consider further. And I'll get your question here in a second, Sage. And then this butene here, 1-butene here, it's not cyclic either. Even though these 2 carbons are sp2 hybridized, we don't have to consider that for aromaticity because it's not a cyclic nor planar bond. So Sage asked the question, what does the N stand for? In the N, this is kind of the abstract part of this, of Huckel's rule, is the N is an integer. So you want to consider the different scenarios where N equals, say, 0, which means you'd have 2 pi electrons. Or if N equals 1, you have 6 pi electrons. N equals 2 is a case where you'd have 10 pi electrons. And we'll see a couple more examples here to hopefully sort that out. So why don't we actually go through, all right, great, excellent. Let's go through a few examples and see if they meet this requirement. Well, why don't we try about something like this is a compound. So, and this came up on the video here for something else, which we'll see in a second. So if we were to look at this compound, this cyclopentadiene here, we'll assume it's cyclic. Is it, well, I don't think we have to assume it's cyclic, and actually you can see that here. Is it planar? Let's say we don't know that quite yet. Is it conjugated? Here, notice these carbons are sp2 hybridized. However, this carbon here on the top here, it's sp3 hybridized. So as a result, this compound would actually not be aromatic. However, one thing that's actually really surprising at first about this cyclopentadiene is that if you were to take this compound and measure the pKa value for one deprotonation, squeeze that one in here, you would actually find that deprotonation of cyclopentadiene here to form this anion has a pKa of around 16. And I can't hear everyone, but I'm sure everyone is just shocked by seeing that pKa value is so incredibly low. And the reason that is surprising is if you take something like ethane or methane or whatever it might be, to deprotonate this, remember back from the old days of seeing this acid-base chemistry, plus H plus. Here we have sp3 hybridized carbon. There's no resonance, there's no induction to help stabilize this. This has a pKa around the order of 48 to 50. So that means that something in this particular compound here above has changed the stability of this conjugate base, or led to the stability of this conjugate base over orders and orders and orders of magnitude. Just an enormous energetic difference in that something here on the top is stabilizing this anion. So since we're talking about this in the context of aromaticity, let's see if maybe something like that actually holds up here. So let's go back and consider our criteria for cyclic compounds and aromatic compounds. So one, is this compound cyclic? Indeed it is. Is it planar? It could be planar. These two carbons are sp2 hybridized, as well as the two on the right. This carbon here now with the lone pair of electrons could be sp2 hybridized, and if it did, it would actually have that lone pair of electrons in the p orbital. It would actually allow this system to be conjugated. So we'd have a continuous ring of electrons in the pi system, in the p orbitals. And then last, we need to see how this fits with Huckel's rule. So we can count up the pi electrons in the p orbitals. We have 2 electrons here on the left, 2 on the right, 2 of the lone pair. That gives us 6. If I did the math right, 6 pi electrons. And so indeed, this would be something that would be defined as aromatic. So we're going to be dealing with aromaticity and thinking about stability, such as that resonance stabilization with benzene that was discussed earlier. This is a nice example, I think, to really show how much of an effect aromaticity can have on the stability of a compound. And it's represented here by this difference in pKa. But here you have a carbon acid that actually has a pKa like that of water. And so it's just a tremendous effect. Remember, this is a log scale. I don't know, that's 10, I don't know how many orders of magnitude that's going to be, an enormous amount in terms of stabilizing. Yes. A gajillion, I think it is, or something like that. Okay, I see some questions coming in. So the first question, James asked if we know the compound is planar or not. That's a difficult one sometimes to see. So a lot of times for these compounds, we're going to first assume that it's planar. I'll show you an example of anti-aromaticity where it's not planar, but we'll first assume that it's going to be planar. And if it's not, then we'll make some other considerations. Okay, excellent. And then Crystal asks if it's aromatic overall. Oh yeah, or if it's only aromatic when it's in the other form. So that's a great question. So there's going to be some cases where, so benzene here is an aromatic compound, and it doesn't matter which resonance structure you draw in, it's always aromatic, right? Because resonance structures are not changing back and forth. They're all there at the same time. However, like you asked, I think, or suggested here, when we consider this compound down below, the cyclopentadiene and deprotonating, the protonated species, the acid, is not aromatic. However, by deprotonating it, you form an aromatic conjugate base. And by forming this, going from not aromatic to aromatic, that's going to be highly energetically favorable, which is then represented by the ease to deprotonate this energetically with the low pKa value. Compared to something like down below with ethane, where it's not aromatic, it's not aromatic. So hopefully that helps. So a lot of new information here. We're going to go through a few more cases with cations. It doesn't just have to be anions, but cations, and then also some heteroatoms, oxygen, nitrogen, and sulfur. And you'll see there's a very systematic way of evaluating these compounds. So why don't we pause here for about 6 minutes this time?